All right, a couple of housekeeping things that I want to make sure I go over. So first is you guys have picked up quite a bit of paper from me. If you haven't been here any of the previous days, come up here and check to see if you have all of the handouts that I've given out. So I gave out a secondary topics worksheet, 2012, 2014 multiple choice test, formula sheets, and the answer key for the 2012, 2014. And then this here is just additional resource for you to get some extra practice. So none of this is required. It's not for homework. The only thing that I'll be checking is what you have already, the 2016 to 2021 FRQs that we've been working through this whole week. Okay. So I want to point out a couple of things on my website. Make sure that you have know where to find everything as you're studying this weekend. So this week we've been going through all the FRQs. The solutions are on the website. I've been doing half the FRQs in the morning and then the other half as help sessions in the afternoon. So hopefully that if you're stuck on any of the problems, hopefully between the key and the video, you have your questions answered. But at any point in time, you can always reach out to me through Remind, and I'll be able to respond to you if you have any questions. So the miscellaneous, the secondary topics worksheet key is on the website under today's link. Under today's dates. You guys just received back your multiple choice tests as well as your FRQ quiz. So I have a couple of different versions. So I will upload those versions up on the website. So if you're wanting to see why you got something wrong or the steps to for the corrections, so that you understand what you missed as you prepare for the AP exam, I will upload this later today and you can find that there under today's date. Okay. Help session. I'll do help session Saturday from 8 to 10 at night. If you can't make it, I will have the video. I'll record the video, but also send out a Teams link. I'll be going over the 2012, 2014 multiple choice, but I can also answer any questions that you have. Anything that's AP related, AP exam related, I can answer that. Okay, on Sunday, I will go have a help session on Teams as well. I will send out a link to that and record that Teams session as well. I'll be going over 2014 multiple choice, but this is a last minute thing. So if you have any other questions from any of the packets, I can help answer that as well. And under Sunday, I also have these videos and solution keys for the thick packet that you just picked up. So the first portion is the AP Classroom multiple choice practice test. Then there's an AP Live review worksheet from previous video sessions that AP College Board has put up to put together. And then verifying differential equations. These are problems that it's solving differential equations, but it's from a different perspective, and it's nice to look through. I didn't really go over it in class, but it's nice to look at it and see if that makes sense. They've shown up before on the AP exam, so these problems. And I think at the top of the page, I put I kind of gave a little table of contents in terms of where those are. So the pages, I think it's the last few pages in the packet. Also in that packet, I put the multiple choice formula sheet that I gave you as you're taking the test. So I think that is a good one to look through and make sure that you know all the formulas, right? The AP, you're not going to get a formula sheet on the AP exam. The only thing you're going to get is potentially they'll give you volume formula or surface area formula for different geometric shapes, and that's it. Okay. So review through your derivative rules, review through your formulas. I try to compact as much as I can onto that multiple choice formula sheet. But you also have a blank formula sheet that you can practice all your derivative and integral rules. And if you have any questions off of any of these packets, I'll more than happy to answer them in either the help sessions on Saturday or Sunday. Okay. Okay, so your AP exam is Monday. Hopefully everyone has this tips and exam details and exam tips. Does everybody have this? I handed this out a couple of weeks ago. Okay. All right, everybody have it. So I think it's good to look through it. I know I'm asking, giving you a lot of resources. I know this weekend is busy. You probably don't have as much time as you would like to prepare, but if you have only minimal time to prepare, then look through the formula sheets. Okay, maybe you don't have time to work through all the problems, but at least look through the solutions for as much of the content as possible, right? Look through the solutions of if you haven't done any of the 2016 to 2021 FRQs outside of class, at least look through the solutions and see if you can read the problem and just visualize what steps you think you would take. If you don't have time to do the 2012 or 2014 multiple choice test, look through the solutions and see if you can read the problem and just kind of gauge if you can decide what type of problem that is and what steps you would take, and then look at the solutions and see if that matches up, right? You can still gain a lot of review just through looking at the solution key, even if you don't have time to do a lot of problems. Same thing here, right? All these worksheets, if you don't have time to work through them, click through the solutions and see if those problems make sense, right? Yeah, make sure you bring your calculator. You can bring 2 calculators if you like, but technically the 36 Pro is not on the approved calculator list. So if you bring this, you're just taking a chance. We don't know if the proctor is going to tell you to put it away or whether they'll allow it. So just keep that in mind. So the safest thing to do is you have your graphing calculator, because you won't get provided one, and I don't have any ones to loan out. So, but I'll send out a reminder this weekend. If at any point you have any questions about Monday's AP exam, or about any questions from your quiz or your test or your worksheets, yeah, feel free to send me a remind, and I'll answer back as soon as I can. Next week, I will be taking attendance. I understand that there's nothing more that I have for us in the class. The last grade in the grade book will be just that 2016 to 2021 FRQs. So if I don't see you next week, then you can still send me pictures of your work, and as soon as I see that, I'll enter them into the grade book. Right? There's no penalty for late work for this 2016 to 2021 FRQ, but after next week, if I don't receive it, I'll put a 0 in the grade book so you can see what that grade is going to be if you don't turn it in. And then once you turn it in, I'll update that grade. Okay, so you can either bring it in or you can send it to me to remind. Just make sure you can send to remind. You send it 1 page at a time. Okay. All right. Any questions about everything that I've kind of talked about and shared? All right, so why don't we spend time going over the 2016 FRQs, at least the first few. So turn to page 27. Okay, number 1, water is pumped into a tank at a rate modeled by WFT, or T is measured in hours. Water is removed from the tank at a rate modeled by RFT, liters per hour. So water is pumped into the tank by this equation, this rate of WT, but then R of T is provided by just that table above. Okay, select values of R of T are shown. At time t equals 0, there are 50,000 liters of water in the tank. Part A says estimate R prime of 2. So that's just, we don't have a function to find the derivative, but we do have order pairs from R of T. So next best thing is slope between endpoints, or slope between points closest to 2. So we'll choose 1 and 3 and find slope between those 2 endpoints. Okay, so change in R of T divided by change in time. Yeah. R is already in terms of liters per hour. So if I want to find the rate of that, then it'll be negative 120 liters per hour squared. Now, this problem is not asking you to justify or to explain the meaning of your answer. But if you were, then you would say that the rate at which water is leaving is decreasing at negative 120 liters per hour squared. So that's how you can let the graders know that you understand the second derivative, right? So don't mention acceleration, don't say rate of a rate. Rather, you're going to say the rate is decreasing. Okay? The rate at which water leaving is decreasing. When you say rate and decrease, combination of those two words is going to demonstrate your knowledge of that scenario. Okay. All right, part B. Use left-Riemann sum with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours period. Is this an overestimate or an underestimate of the total amount of water removed? So left-Riemann sum. Okay. Subtract each of the subintervals there. So 1 minus 0, 3 minus 1, 6 minus 3, 8 minus 6. And then your width was going to come from that top highlighted row. And then the bottom row is going to be where you pick up the height, right? And you do width times height all the way down. Okay, so we should get 8050 as the area, and so that's our approximation. That between 0 and 8 hours, 8,050 liters of water has been removed or has been drained from the tank. It's also asking if this left Riemann sum that we found is an over approximation or under approximation. Well, at the top of the page, they tell us that the graph is decreasing, right? So if you have a decreasing graph and you're letting every rectangle be connected to the curve by the left endpoint, then all those rectangles are going to have portions that stick up above the curve. So all those rectangles is going to create area larger than the area under the curve itself. Okay, so answer is overestimation. Part C, use your answer from part B. You can find an estimate of the total amount of water in the tank to the nearest liter. So we've seen this problem over and over again, right? Where this is going to be a rate in, rate out antiderivative word problem, where any total amount that we're looking for is going to be a couple of moving parts, right? The initial amounts plus the amount added minus the amount removed. So if we build it specifically for this scenario, then we can say that the total amount that we're looking for, the amount of water A of t, is going to be made up of a couple of information, right? There's the initial amount that we're starting with. There's the amount added, which is given by that W of x. Now, W of t is a rate, so we got to take the antiderivative of that rate. So I go from 0 to t, integral from 0 to t of W of x, just to show that there's a different variable there. And then R of x or R of t is going to do the job of taking water away from the tank, removing water from the tank. So minus integral from 0 to t of R of x. But now that we have our formula, we can adapt it for part C. We want to find out how much water there is 8 hours in. Okay, I think my key is a little bit off here. The integral from 0 to 8 of WT should show 7836. I think on my key I had it as 5736. So we start off with 50,000, and then water added into the tank is 7,836 liters. And then we don't have a formula to enter in for R of t, but we gather that from part B, right? We approximated using that Fremont sum, so we'll use that value. The approximation is 8,050 liters. That's been removed from the tank, and then we just combine those values together, and we get 49,786 liters, 8 hours in. Yeah. Yeah, yeah. Yeah, it's find an estimate. Yeah, you're right. Our estimation is, but it's okay. They won't take off points with the equal sign, but I can see your point. Yeah. Okay. Technically, it is an approximation because even though the first two are exact, this is not going to be exact. Yeah. All right, for part D, is there a time t when the rate at which water is pumped into the tank is the same as the rate at which the water is removed from the tank? So we basically want to know, when is W of t equal to R of t, right? When is the rate going to be the same? But the issue is that we don't have the ability to set the equations. I mean, normally this is what we would do, right? We would find the derivative. A prime equals W of t minus R of t, set equal to 0, graph the two functions, WT minus R of t, and see where the graph crosses the x-axis, right? Normally we would do that. That's fine for W of t, but R of t, we're kind of restricted because we don't have all the in-between points. We just have these select values. So how do we work around that issue? Well, We do know that this is a continuous function. And maybe what we can do is we can find what's happening at the endpoints, right? And the idea is that if I find the rate at which the rate of the water level is changing at the beginning and at the end, maybe I can gather some information. So if I found the rate at which water is entering in at 0 and the rate at which water is leaving at 0, 2000, that can come from the calculator, and then the 1340 is coming from the table. If I subtract that, I get a positive value. So that means at the beginning, water is rising, right? Water is rising because my rate is positive. But then if I figure out what's happening at 8 hours in, 8 hours in, W of 8 minus R of 8, if I enter 8 into my WT function, I get 81.3. If I look at R of 8, the rate at which water is leaving, 8 hours in is 700. If I subtract them, I get a value less than 0. So the water is rising at t equals 0, but then it's falling at 8 hours in, which means that somewhere in between, there must be a time when that water level is transitioning, right? Where it's not changing, right? It's got to stop for a moment before it can start falling. And so this is applying IVT. Okay. So intermediate value theorem tells us that if my target that I'm hitting is falling between my starting and my endpoint, then that goal must be met somewhere, right? If we're starting with a value that's negative or positive, sorry, and we end up with a value that's negative, then somewhere in between, that value that we're trying to look for, that 0 value we're looking for, has to be reached, right? Because we're told that the function is continuous. R of t and WT are both continuous. So by IVT, there must be a time t between 0 and 8 where WT minus R of t is equal to 0.
Is there differentiable? Because they're differentiable?
It's because they're continuous. Now, the differentiable means that it's a smooth curve, but in this case, it's not that important because as long as the function is continuous, we know that it's not going to jump from positive past 0 into the negative, right? That's all we need. The only time we really need that differentiable restriction is if we're trying to guarantee a slope. If it's like a mean value theorem or Rolle's theorem, then we do need that differentiable. But here, they are saying it's differentiable, but from our problems, we really don't need that information. Okay. Okay, any questions with number 1? Okay, look at number 2. Number 2 is a particle motion. It's one of the easier problems that you'll see. Hopefully, you'll see something like this on the AP exam. All right, read number 2. This is also calculator active for number 2. Okay, for t greater than or equal to 0, a particle moves along the x-axis. The velocity of the particle at time t is given by v of t. Particle is at position t equals 2 and t equals 4. At what time t equals 4, or at time t equals 4, is the particle speed increasing or decreasing? Speeding up or slowing down? So increasing speed, decreasing speed, this is what we're able to show our work by comparing velocity and acceleration, right? So what we can do is we can find the velocity at 4, find out whether it's positive or negative, make the calculator do the derivative for us. So if we do math 8 and derive, we can make the calculator find the acceleration at 4. And then we compare their signs, right? If I'm looking at same signs between velocity and acceleration, then I know the speed of this particle is increasing. But if velocity and acceleration have different signs, then we know that the speed of this particle is decreasing. So for part A, we can say that this particle speed is decreasing since velocity is positive and acceleration is negative. Okay. If you're having trouble getting that value to show up, let me know. I can help you, but it's going to be math 8. Either you, if you're using 36 Pro, you can use that second d over dx, make the calculator find the derivative at that point, or on the calculator, it'll be math 8, right? D over dx, velocity function at t equals 4. Part B, find all the times t on the interval from 0 to 3 when the particle changes direction. So particle changes direction when velocity changes signs. So we can just graph our velocity function and see where it crosses the x-axis. So I have it under y2, 1 plus 2 sine x squared over 2. And then before I graph it, I like to go to the window just to see if I can make some adjustment with my interval. I know that the solution I'm looking for is between 0 and 3, so that makes it easy for me to set up my x value interval. I'm just going to go from 0 to 3. And then I like to typically leave my y min, y max as negative 10 to 10. I can always go back and change it if I realize it's too zoomed in or too zoomed out. But that's where I like to begin. Okay, sketch your graph. We do see an x-intercept, so we know that velocity is 0 at this point, and it crosses the x-axis, so that means it's moving to the right, stops, moves to the left. That's a change in direction. If that we find that x-intercept, we find the point when the particle changes direction. So if we do second trace, 0. Choose a point to the left of the x-intercept, hit enter. Pick a point on the other side of the x-intercept, hit enter. 2.707. Question?
How do you get the table?
Okay, so to get the table up on that, yeah, you're going to go to table, edit function, type in that function. Maybe you want to start at 0 and then your step, you want to tell them how what the interval for your order pairs. Maybe you want to start at 0.5. And then you can kind of step through and look at your y values and see where your y values change the signs. And if you're wanting to get even more accurate, then you can go back and change your step to even smaller interval, like 0.1 or 0.2. Part C, find the position of the particle at time t equals 0. So anytime I'm looking for position and I'm given a starting point and I'm given velocity or given a way to get displacement, then I'm always going to go back to this formula here. Final position equals initial plus displacement. Okay, very useful in a lot of situations. We can also adapt this one derivative down. We're asked if you're given a starting velocity and looking for ending velocity, and if you have information about acceleration, we can just shift everything one derivative and say final velocity equals initial velocity plus displacement, or the integral of acceleration. So on your formula sheet on the back of the thick packet, I have those variations listed out. So good to try to look through as much as you can. Okay, something we have to be careful about, I mentioned this the last couple of days, is if you're having to go backwards, make sure that your initial and your lower bound of your displacement is matching, right? Even if you're going backwards and you feel like, oh, I'd rather go from 0 to 4, you can do that, but don't do that initially, right? Go ahead and set up the way that the formula is supposed to be set up. And if later on you want to change the bounds, you can always change the bounds later and then adjust with a negative in front. But you got to make sure that your initial and your lower bound are matching, okay? Because you're starting at 4 and you're ending at 0. So you need to reflect that in your displacement integral. But I would say that in this case, it's not worth the trouble to try and change the bounds because the calculator will make that adjustment from 4 to 0. Now, if you're having to read the graph, then I would adjust the bounds and change the sign. But I mean, you'll get the same answer either way if you flip the bounds and change the sign, but the calculator can do that for you. So I'm only changing the bounds if I'm having to read the graph of my derivative, or if I'm reading my derivative graph. Okay, any questions for part C? Okay, part D is pretty easy. It's asking for the total distance from 0 to 3. Total distance is just the definite integral of my velocity. Definite integral of the absolute value of my velocity. So don't get thrown off between total distance and displacement. Sorry, in final position. With total distance, we don't add the initial point. Okay, we just want to know how much back and forth did this particle travel. We don't care where he starts. Right? We just want to know how much did he move in that time interval. You can reach your absolute value by going to math ABS or math number ABS. All right, any questions so far? Okay, let's look at number 3 on page 29. Okay, the figure shows the graph of the piecewise linear function from between -4 and 12. The function g is defined as g of x equals the integral from 2 to x of f of t. Does g have a relative minimum, a relative max, or neither at x equals 10? So as soon as we see this relationship, we know that G and F are not at the same level, right? F is really sitting at a level below G because it takes the integral of F to make it even the same level as as G. So because F is sitting at one level below G, we know that this F graph we're seeing in front of us is really another way of saying this is G prime. Okay, graph of F is the G prime graph. Okay, so if we're looking at the derivative graph, we like to go ahead and label what we're working with here. Above and below the x-axis represent the slope of the original graph. Let's go ahead and create the sign line that we can use later on. We know that our endpoints is from -4 to 12. And really the only relative max and relative min that we're going to see, even though we see a bunch of slope zeros, is when only if this the graph changes signs, right? So here at 2 and 10, even though these are hitting the x-axis, they're not crossing over to the other side. So that means there's not going to be a change in slope, which means that neither are going to be relative max, relative min. So the only relative max, relative min we're going to see are at -2 and at 6. Okay, between -4 and -2, we see the graph, our G prime graph is sitting below the x-axis. So we know all that's going to represent different variations of negative slope. Anything between -2 and 6 are all sitting above the x-axis. So that's all going to represent positive slope. And then between 6 and 12, all below the x-axis, so negative slope. Okay, does G have a relative min, relative max, or neither at 10? So we can tell that, okay, 10 is neither a max nor min because there's no change in sign. For part B, does the graph have a point of inflection? Okay, so if you're looking at the derivative graph, your point of inflection is going to show up as peaks and valleys. So all these peaks and valleys are all points of inflection of the original graph. Okay, so the answer is yes, there's a point of inflection at x = 4, since f changes from increase to decrease. Okay, another way of saying that there's a peak or valley. Okay, part C. Find the absolute minimum value and the maximum value on the interval from -4 to 12. Justify your answer. So this is basically asking us to apply EVT. So EVT says test endpoints and test critical points. So the critical point that we care about is just going to be -2 and 6, right? The other critical points are not relative max, relative min. So the only candidates we care about are the endpoints and relative max, relative min. So we have 4 points that we're going to test, and we're going to be using the formula that's provided for us. Now, sometimes there are problems where you got to do final equals initial plus displacement, but then there are other times when you're just going to use the formula that they give you. So depending on what's given to you, that's how you're going to approach finding order pairs. If they give you a formula, then follow that formula. If they don't give you a formula, but they give you a starting point or initial point, then you do final equals initial plus displacement. Okay, so some of my students get thrown off like, wait, which one do I use? You use whichever they provide you. Okay. Okay, so we need to find our endpoints and critical points using this formula. So we can find, we'll find g of -4. Right? We'll find g of -2. We'll find g of 6. And we'll find g of 12. Okay, so g of -4 is the integral from 2 to -4. I'm always going to follow whatever the rule says, and then I can decide whether I want to do anything with the bounds. So I'm going from 2 to -4. These are all geometric shapes that we can find. These are all triangles that we can find areas of. But we're going backwards here. So because we're going backwards and I want to pull information from my graph, I would rather read from left to right. So I'm going to adjust the bounds and change the sign. And I'm going to start totaling some of these values up. Okay. Now you see triangles everywhere, but you want to make sure that you're looking at the correct places for these calculations. Even though there are triangles that you see everywhere, some of them are not part of our diagram. So here, we're only looking at what's between the graph and the x-axis. So let me highlight the only parts that we are really looking for area here. Okay, so first is below the x-axis. So this is 1/2 base times height. Base is 2, height is 4. 1/2 base times height, 8 divided by 2 is 4 below the x-axis. So I can say this is -4. Okay, so these are all the same triangles here, right? This here is also, that's 1/2 base times height, that's 4. I'm going to separate everything. I could combine a bit more, but kind of helps just having as much information as we can in case we need to find those intervals. These are all negative, right? Okay, let's go ahead and find those points here. So from -4 to 2, -4 to 2, it's going to be -4 and 4 cancels out. I'm just left with +4, but I already flipped the bounds, so there's a +4 with a negative in front, so -4. G of 6 is from 2. Sorry, let's do G of -2. G of -2 is from 2 to -2, right? We're following what the rule says, right? 2 to -2. It's the upper bound that we're changing initially. Okay, I'm going to flip the bounds here so I can read from left to right, pull a negative out. So from -2 to 2, this is a +8, but then I changed the sign there, so it'll give me a -8. G of 6 is a definite integral from 2 to 6. From 2 to 6, that's 8. No change in signs because I'm already going from left to right. And then G of 12 is from 2 to 12. So 2 to 12 is 8 minus 8, which is 0. 0 minus 4 is -4. So we can say absolute maximum is 8, absolute minimum is -8. And your work that you're showing here is justification, okay? There's no additional words. You don't have to mention EBT if you don't want to. Okay, part D, between -4 and 12, find all the intervals where the original g of x graph is less than or equal to 0. So I think the best way to do this, it feels a little bit tedious, but why don't we just plot as many points as we can, maybe even some of these points that are non-relative max or relative min, just so we can get a clear picture, right? If we can if we can plot out as many order pairs as we can, then visually it's a lot easier to find where the graph is sitting below the x-axis, right? We already have some points to begin with, but let's see if we can gather more points after we sketch out what we have. So for part D, I'm going to just plot as many points as I can using this formula to get to my order pairs. So I have -4, -4. I have -2, -8. I have 6, 8. And I have 12, -4. Okay, let's see if we can find some more order pairs here, because right now we kind of have an idea how the graph is moving, but we don't know where it's going to hit. So let's find some other order pairs here. Why don't we also find the order pair at 2? Okay, let's see what happens at 2. So g of 2 is the integral from 2 to 2. And if my bounds are ever matching, I know that I haven't moved anywhere. So that's going to be 0. So I know g of 2 is 0. Okay, so I have an idea how my graph is going to move, right? My graph is going to, those are my anchor points here. I have an idea that my graph is going to be rising to that point. Okay, from there, we know it's going to go up to 8, but then it's going to come down. Sorry, 6. At 6, it's going to hit a point there. Why don't we also figure out where 10 is, right? We know the graph is decreasing, but what's happening at 10? So let's find g of 10. So g of 10 is the integral from 2 to 10. So 2 to 10 is 8 minus 8, which is 0. So that's good. Gets us back to 0. Sorry, this should be over here. So 10, we know the graph hits 0. So we know our graph is going to have to come down here and then reach down. So now we have enough information to confidently say where our graph is below the x-axis, right? Below the x-axis from starting point until 2, and then from 10 to 12. Well, the endpoints, the graph hasn't started moving yet. So whenever it's increase, decrease, I always do parentheses. I think the only time I do brackets if it's asking for like domain or range. But if it's interval of increase, decrease, I always do parentheses, yeah. Or, sorry, if it's particle motion. If it's particle motion and it's asking for, when is velocity less than or equal to 0, sometimes you got to test the endpoints to see if the particle is already moving. But if it's a graph, I just always use parentheses. Okay, so we got through 1 through 3. 4 is differential equation. 5 is kind of strange. It's It's a disc washer method problem. You got to turn it sideways to see the fact that this is the axis and you're rotating in that region. And then number 6 is just chain rule, quotient rule, and first theorem. I'll go over these in the afternoon. I'll make a video of it, and I'll send out a remind link for Teams if you want to join for help sessions. Okay. Guys, if you have any last minute questions, feel free to send me through remind. Hoping that if you can join either of the help sessions, that'll be good to do some last minute prep as well as help answer any questions that you have. But hopefully, with all the packets I'm giving you, all the solution keys, all the videos, hopefully that'll be good resource for you guys as you do some last minute preparation for Monday.
This one, where we're set the sequence 0 to 100. It would be both -10 and 10, right?
Yeah. Both
And then we
and
would
10.
create.
Yeah, so you're summing it, yeah.
And
That's your info with the derivative.
Gotcha.
Yeah. Okay, all right. Thank you. Here, hold on this, or do you want to?
We used it as I was going through the thing to practice.
Good. All right, thank you. I'll mark it down.
I think I'm sure you have homework.
Yeah.
So I have tried IT numbers
Okay.
because, so.
Sure. Have a good weekend, guys. Do some last minute studying and good luck on your exam on Monday. Thank you.
I need to finish it.
Great, got it.
I did a 24.
The second part, I feel like it's
I didn't have to.
Okay. Yeah, I made that okay here, so I will change that in the thing. Okay.
Thank you.
Mhm.
Have a nice weekend.
All right, good luck. Okay, yeah, you want to make sure that your plot is, for some reason, I don't know, plot is highlighted and it's not going to correct. You got to go and highlight those plots.
Thank you, Sue.
Okay, good luck. Here, Ruby.
This one. Number 2.
Okay, so e to the x over 2, and ln x equals 2. So e to the x over 2 is going to kind of look like this. And we're going from 0 to it's just the area, right?
Mhm.
So it's just top minus bottom.
Oh.
And then go to do substitution and then plug the number lower. All this is.
Yeah, I saw it. Oh, that's not mine?
This is, yeah, so, that is from previous training, so I'll give you this. Sorry, I didn't pick up from last year.
This one too.
Got it.
Oh. You just got to 40-page packet. Another one? Yeah. Thank you.
Yeah. Amazing. I have to go.
Come on. You're 5. Are you gonna do this one? The exam's on Monday. Figure it out.
I'm so